Yay!
Yay! All right, here's a slightly more complicated example. What we're going to do here is suppose that we have a piston, like a cylinder of gas with like a metal plate on top. Suppose the metal plate just doesn't weigh very much, so we don't have to worry about it. And it's at ordinary atmospheric pressure, it's suspended. So here's the initial position of the plate, and it's suspended at this height h naught above the bottom. All right, and then the idea is what we're going to do is we're going to put a mass onto the plate, and that'll sort of squash the air down. So what we want to do is find what this final height h is of the piston. How much does it compress is what we're really trying to find out. Okay, so we add that mass, and then we want to find the new height. Let's start by looking at like Newton's laws. All right, so after we put the mass on, what do the forces look like? What are the forces going to be on that piston? Well, what is the force going up? That'll be the positive force. The force going up is just going to be the force caused by the gas underneath, right? And then what's going down is just going to be mg, the weight of the mass that we put on there. And also, there's going to be the atmospheric pressure, right? That's also pushing down. Okay, so those are the forces. So they're all going to combine to be 0 after we put the mass on, and this plate is sort of suspended, height h above the bottom. Let's write this in terms of pressures, so we can use the ideal gas law. Okay, well, what's a force? Force is pressure times area. Okay, so let's call this the pressure of the gas times the area of the plate. Move the other two terms to the other side. So this is just going to be mg plus atmospheric pressure. That's just going to be, let's just call that P naught, right? The pressure of the atmosphere times the area of the plate. All right. So after we do that, let's see, what is our ideal gas law? PV is nRT. Okay, so for PG, let's just put in nRT over the volume times A is mg plus P naught A. Okay. So for this, what we're going to do, what is that? Okay, what is the volume here? After this thing has squashed down a little bit, what is that volume? The volume is just going to be the area of the plate times h, right? So that's how we're going to get h in here. This is going to be the area of the plate times our new height h. Okay, so this is going to be nRT over h. And look, we had an a up top, so those a's are going to cancel out. And so this is just going to be mg plus P naught times 8. Cool. Okay, let's solve for h. See what we got. So h, our new height. So 1 over h is equal to mg plus P naught a over nRT. So let's just flip it. Let's flip both sides. So this is going to be nRT divided by mg plus P naught a. All right, cool. Oh, further, let's go a little bit further. What about the n? That little n. So maybe I don't know the number of moles of the thing that's in there. So further, let's say that, okay, what is this n? This n I have up top, nRT, I've got nRT up top. nRT is equal to PV. Okay, but look, our temperature hasn't really changed. Let's suppose that the temperature hasn't really changed. And what else has happened? The R, that's just a gas constant. The N, I haven't changed the number of moles. I'm not allowing gas to escape or anything. So nRT is going to be the same quantity. So what I'm seeing is this PV is just the same as P naught V naught. That'll help. Okay, so what we've got is that nRT is just P naught A H naught. That'll be really handy. So, okay, let's plug that in over here. So we've got H is equal to, okay, if I flip that equation over, I've got nRT, but we said that was P naught A H naught, divided by mg plus P naught A. Okay, let's divide everyone by P naught A. That looks like that's going to be that's going to make things a lot easier. So that's just going to be, let me have that H naught here on the outside, and so that's just going to be 1 over mg over P naught A plus 1. How about that? That looks a lot easier. Okay, so over here I've put in M is 10 kilograms, H is 10 centimeters. Let's say that the radius of this thing, I don't know, 5 centimeters, something like that, right? So the A would just be pi r squared. So when you put these numbers in, what you're going to get is H naught times about 0.87. So what that means is that this thing is going to squash down like 13%, something like that, right? It's going to be 0.87 of what originally is, or it's going to be something like the 8.7 centimeters here at the end. So sure enough, it's going to squash down a little bit when we put that mass on it. Maybe not quite as much as you think. It's kind of hard to compress air. So putting a 10 kilogram weight on that thing, 20 something pounds, only squashes it down by a little over a centimeter. So that's maybe a little bit unexpected.